Hello and welcome to the session on the modeling of pore water pressures in the PLAXIS LE software. My name is Murray Fredland and I will be walking you through the methodology today. Our video today will involve a brief overview of the use of pore water pressures and then cover the primary methods of analyzing a slope stability model. We will look at total stress, effective stress, and unsaturated analysis methodologies. We will also look at methods of combining the modeling of positive pore water pressures and soil suctions. We will look at the methods of modeling rapid drawdown scenarios using the Duncan method or the combined finite element method. Lastly, we will look at how these methods can be extended into the realm of 3D numerical modeling. It's helpful to first examine why it's important to consider pore water pressures in our numerical model as geotech engineers. The primary reason is that historically changes in pore water pressures are the most common cause of slope failures worldwide, as noted by Duncan in 2005. Therefore, the consideration of pore water pressures is an important aspect in our numerical modeling process. It should also be noted that suctions can physically influence the results as well, and it is worth considering how we include the effect of these suctions. This presentation will review the correct methodologies from going from field data to pore water pressure representations in PLAXIS LE and how do we integrate stability and groundwater. We will cover the primary three methods of analysis, which are a total stress analysis in which we do not consider any pore water pressures, effective stress analysis where we consider the effect of positive pore water pressures, and lastly, an unsaturated analysis where we consider both positive pore water pressures and the effect of soil suctions. If the user does not select any pore water pressure conditions in the model, then the software defaults to a total stress analysis. In this model, the pore water pressure objects are not defined and all constitutive models consider only total stress. It's worth noting that soil suctions are not considered and unsaturated constitutive models would not consider suctions, but only consider total stress. An effective stress analysis is automatically enabled in the software if the user defines any pore water pressure conditions in the numerical model. The pore water pressure conditions are found under the pore water menu, and there are multiple methods available. Once the user defines a method of representing pore water pressure conditions, all constitutive models in the software consider effective stresses. Suctions are ignored and on all constitutive models except the unsaturated soil models. Unsaturated analysis considers the effect of soil suctions on the shear strength of the soil above the water table. This type of analysis may be enabled in the software through defining two aspects in a model. Firstly, water objects must be turned on and a zone of suctions must be defined. Then unsaturated constitutive models must be enabled in the regions that are above the water table. All constitutive models consider effective stress below the water table. It's worth noting that unsaturated constitutive models which are applied below the water table would not consider the unsaturated portion of the constitutive model, only the saturated part. There are a variety of ways of considering pore water pressure in the software. The software can implement a single water table or multiple piezometric surfaces, which can be applied to different regions in the model. The software also offers a discrete points method or a combined water table and discrete points hybrid method. R sub u values can also be utilized and pore water pressures can be imported from a related finite element seepage model. Rapid drawdown is handled as a special case in which there are two methods to analyze the specific problem. The software currently offers the Duncan method as well as the combined effective stress, finite element seepage, and limit equilibrium slope stability method. The software allows water tables to be defined both internally and externally to model regions. If the water table line goes outside of the defined regions, then the water load is represented as a load against the slope equivalent to the water head load. Only one water table is allowed per model. Multiple piezometric surfaces can be defined internally and externally to model regions. The pore water pressures defined by these piezometric surfaces can be applied to one or more regions in the slope. Therefore, each region can theoretically have its own definition of piezometric head that varies laterally in the model. It's common in the field to measure the water table with piezometers. Such measurement methods measure a waterhead at a depth and imply a theoretical water table above them. Such measurements, however, do not strictly define a water table. Therefore, it's often optimal to represent piezometric data as a series of discrete points in a model and then interpolate the resulting field of pore water pressures. The interpolation method will project between points and result in a spatially varying water table that is not required to be hydrostatic. The hybrid method allows the user to define pore water pressure regime using both a water table and a discrete set of points above the water table. Below the water table, the pore water pressures are interpreted to be hydrostatic. The suctions or perched water tables defined above the water table line are interpolated using one of the methods that can be selected in the software. The R sub U method allows the pore water pressures to be defined as the ratio between pore water pressure and overburden stress. R sub U coefficients can be set to override a selected pore water pressure method. The definition of R sub U values is shown in equation 149. The B-bar method is also implemented in the software to define excess pore water pressures in a particular layer. In the figure below, it shows the calculation of total head in a 3-layer system. The water table is measured to be halfway up the top soil layer, as denoted by soil number 1. The head at a particular point halfway up soil 3 is calculated as the sum of 3 separate pressures. Firstly, the heads above the points are added together and multiplied by the unit weight of water to get a hydrostatic pressure. Then the excess pore water pressures present in soil number 2 are calculated using the B-bar value entered. Lastly, the R sub U pressure entered for soil number 1 is added into the equation. This results in a calculation of total head. Pore water pressures are ideally imported into a stability model as calibrated to field conditions at a site. This can be accomplished using the seepage model present in the PLAXIS LE software. In this scenario, the seepage model is calibrated and then exported to the stability model. Pore water pressures at every node point are transferred to the stability model. Unsaturated suctions are only considered if unsaturated constitutive models are utilized in the software model. The software also implements the 3-stage rapid drawdown procedure as suggested by Duncan in 2005 to estimate the factor safety under the condition of rapid drawdown of a water table in an earth slope. The 3-stage method is available in the software and has been implemented for both 2D and 3D analysis. An example of the use of the Duncan method can be seen in this practical example. The Duncan and Wright 3-stage procedure is utilized in this case to analyze a changing water table against the slope. Non-circular slip surfaces are utilized to analyze the conditions. An ultimate factor of safety of 1.14 is calculated in this case. If the hydraulic conductivity of the soil is known, then the time lapse to draw down pore water pressures in the slope can be computed using a seepage model. These 3 figures show the change in the water table over time. In this scenario, the change in water table is minor given the hydraulic conductivity present at the site. On other sites, the rapid drawdown effect may be larger. If we take the calculated pore water pressures from the seepage model and import them to the stability model and then calculate an updated factor of safety at various points in time, we can see that the location and the shape of the slip surface changes as a result of the change in pore water pressures within the slope. It should be noted that all the principles discussed in this talk are applicable in a 3D analysis. This facilitates the relatively simple ability of the software to extend a 2D model to a 3D model, which captures the site reality more completely. This extension to 3D is possible applying all the same principles in the analysis. The primary differences are that the boundary conditions can change in 3D in the seepage model, and the geometry is likely to have some inherent 3D effects which influence the shape of the slip surface as well as the location. In summary, we have found that pore water pressures are one of the most important considerations in slope stability analysis. There are 3 primary methods of analysis which include total stress, effective stress, and unsaturated analysis. There are multiple methods for considering positive pore water pressures or unsaturated suctions above the water table. These methods have been defined in this presentation. Advanced constitutive models are available to manage the influence of unsaturated suction and its contribution to shear strength. It should also be noted that all of the same principles discussed in this video apply when integrating seepage instability in a 3D analysis. Thank you for your time and your attention today. This concludes the video on pore water pressures.